In this section, we're going to look at inverse functions. Inverse functions are functions that undo each other, okay? Now, this is the formal definition of an inverse function. If f and g are two functions so that f of g of x gives you just a plain old x, and g of f of x gives you just a plain old x, then that means that g is the inverse function of f. And so the symbols that we will use for that is this f with the little -1. That's called f inverse. So another way you could think about this is f of f inverse of x equals x, and f inverse of f of x also equals x. Essentially, what we're saying is doing this composition erases everything that's been done to x. And if we do it the opposite way, it erases everything that's been done to x. That's the idea of an inverse, okay? In calculus, and you saw a lot of this in geometry as well, but in calculus, whenever we work with a formal definition or with a theorem, we always need to decide what are the conditions that must be met and what is the conclusion that you can draw. So the conditions in this case are where it says, let this be true. The conditions that we have to meet are we have to show two things. First, we have to show that f of g of x equals x, and the second condition is that the reverse of that, g of f of x equals x. If we have shown both of those things to be true, then the conclusion we can draw is that f and g are inverses. There is no other way to prove that functions are inverses. Every year on the test, people do all kinds of crazy things. The only way to prove or to show or to verify that two functions are inverses is to use this formal definition and to use function composition. If you explain your answer in any other way, it will not receive credit because you have not used the definition, okay? So, for example, on number 1, it says, show that these functions are inverses of each other. Show, verify, prove. Those are all the same thing. So the only way that we can show this is by using the formal definition. So the first thing we need to do is meet our first two conditions. So we need to start by looking at f of g of x. So that's going to be 4 times x plus 7 over 4 minus 7. Well, these 4's are going to cancel out. So now we have x plus 7 left, and then we have minus 7. The 7's zero out, and so we get x. We are not done because we have only verified one of our two conditions. The second one now is that we need to show that g of f of x is also equal to x. So we're plugging this in the opposite way. We're going to say 4x minus 7 plus 7 over 4. We can see here the 7's zero out, so we get 4x over 4. We see now that the 4's divide out, and so we are left with x. Side note, you should not do a whole bunch of canceling all in one step, okay? What I see a lot of people do, for example, on this first step, is they just end up crossing out the 7's as well. In the form that line of the equation is written, you are not allowed to cross out those 7's. You are not free to attack those 7's until you get to this line. So you need to make sure that you rewrite it every single time. This is a proof, okay? So you need to overshow, not undershow. Now that we have met our two conditions, we can draw our conclusion. So the conclusion is, so f and g are inverses. Without that sentence at the end, you're not done, because all you've done is show me what you have found. You haven't made a conclusion now about what you know. But this is the idea. These are inverses of each other because when I plug this into g, it takes away everything that has been done to x. And similarly, in the reverse, it takes away everything that's been done to x. That's the goal of an inverse. So that's how we prove that functions are inverses. If I want to find the inverse, I need to essentially do all of the operations in reverse. And so the way that we can kind of calculate that algebraically is you're going to take the original function and rewrite it using y and x. So if you have an f of x in there, switch it out for a y. Then you're going to switch the x and the y. And then you want to resolve the equation for y. If the result is an inverse function, then you can rename it as f inverse of x. So let's look at this first example. First step is to rewrite this using y equals equation. So y equals 7x minus 5. Next step is to flip the x's and y's. So we're just going to trade their places. Now that I've done that, now I need to solve for y, which means rearrange the equation. So I'm going to start by adding 5 to both sides. So I get x plus 5 equals 7y. And then I'm going to divide by 7 on both sides, which leaves me with y equal to x plus 5 divided by 7. That is a function. We don't get any plus or minuses or anything like that. So that means that we can name it f inverse of x, and the answer is x plus 5 over 7. Ta-da! There's your inverse, okay? Take a moment, put the video on pause, and try number 3 and number 4. All right, here come your answers. All right, here are the 2 answers. Take a second to look over those. I think number 3 is pretty straightforward. Number 4, we have to do a little bit more of our fancy rearranging here because you end up with y in the denominator of a fraction. So the first thing that I did was to multiply both sides of the equation by y. When we do that, you can see now that I have y on both sides of the equation. So we rearrange it so that all the y's are on the left. And then we factor out the y and divide by x minus 4, and that's how we get y by itself. So we can rename that now as f inverse of x. Inverses are really important, and there is a quick way to tell if a function has an inverse, that is also a function. Everything is going to have an inverse. Every function is going to have an inverse. But sometimes the inverse does not end up being a function. So we couldn't call it f if it's not a function, okay? The way that we can check that is instead of using the vertical line test to test if it's a function, we use the horizontal line test to test if it has an inverse that is also a function. So just like with the vertical line test, we want to see if it intersects more than once. On number 5A, it intersects twice. So this one does not have an inverse function. Part B, it does have an inverse function. And part C also has an inverse function. There's nowhere that intersects twice. If your function has an inverse that is also a function, then we call that function one-to-one. This is really important vocabulary right here, okay? A one-to-one function is a function in which no 2 different ordered pairs have the same second component. Only one-to-one functions have inverse functions. Therefore, any function that passes the horizontal line test is a one-to-one function. So that's how you can test that a function is one-to-one, by using the horizontal line test. Essentially what this means is that if a function f is one-to-one, then both f and f inverse are functions. What does this do? This guarantees that there is one path from each input to the output, and there is also only one path back from the output to the input. And so that's really important. The graphs of f and f inverse are a reflection of each other over the line y equals x. And when you reflect a point over the line y equals x, it simply reverses your ordered pairs. So every point AB on your graph turns to the point BA on your inverse graph. So it makes it really easy to sketch an inverse. So for A, we want to use the graph of f to find the graph of the inverse. We don't need to do anything with equations or anything like that because we're just going to work with the ordered pairs. This furthest to the left ordered pair is -3, -2, so we want to switch it to -2, -3. This point is -1, 0, so we want to switch it to 0, -1. And the last point is 4, 2, so we want to switch it to 2, 4. And so the graph looks like this. And you can see that it is a reflection over this diagonal line, y equals x. That's exactly what we expect to happen, okay? Now, B says, find the inverse of f of x equals x squared minus 1 for only x is greater than or equal to 0. Well, x squared minus 1 is going to be the parent function of a quadratic just shifted down 1, but we only want greater than or equal to 0, which means we only want the positive half of the parabola. So that would look like this. You can always make an XY table to graph if you're not sure, just like we did with piecewise functions. Start with 0 and plug in 0, 1, and 2, and you'll get those same points. We don't want the negative side because they told us to only stick with this one. So now, if I want to graph the inverse, we just need to flip those points around. The bottom point is 0, -1, so we want -1, 0. The next point is 1, 0, so we want 0, 1. And the last point is 2, 3, so we want the point 3, 2. And so it should look like this. And remember, we said the inverse of a quadratic is a square root, and that the graph of a square root looks like the top half of a sideways parabola. This is exactly why. And so that is what you need to know about inverses, and you have some math lab to practice on.